So this is lecture 3 of previously of the gas loss videos. So make sure that you have watched part 1 and part 2 before you actually watch this video, before proceeding on to this one. So beforehand, we talk about 3 laws. We talk about Boyle's law, which is pressure and volume. All right. So we actually also talk about Charles' law, which is pressure and temperature, and we talk about Gay-Lussac's law, which is about volume and temperature. So in this slide, we're going to be talking about the combined gas law. And the reason why it's called combined gas law is because we're combining, guess what? Boyle's, Charles, and Gay-Lussac's law. So this is a little bit more complicated. Before, when we only had 2 variables, we could actually predict what the answer is going to be. But in this case, since we have 3 variables, it's a little bit much more difficult to do. So you actually have to do at least 1 round of multiplication before you can guess what the answer is. But there are still some rules to know about. Okay, so this is a problem here. What is the new pressure? So we're looking for P2 when the gas that had an initial pressure, so this is P1 of 87.1 atm, initial volume V1, okay, initial temperature, okay, T1, all right, was cooled to 300 degrees Kelvin, that's T2 obviously, and this is volume 2. All right, so again, we know it's volume 2 because, see this words again? 2. So any numbers after the word 2 are final temperature, or final, in this case, numbers, okay? So 2 of something, V2, T2, whatever that would be. Again, what happens is we're going to write out the whole ideal gas equation, and we will eliminate, in this case, variables that is not needed. So there's no moles here. There's no gas constant either. So in this case, we actually are looking for P2 again. And again, the reason why I know it's P2 is because it says, what's the new pressure? So we're looking for P2 in this case. And in this type of math, what you just do is you just basically write out the equation, right? P1 times V1 over T1 equals P2 over V2 times T2. Okay, and again, make sure that your temperature in Kelvin, which is the case in this, which is properly the case for this problem, and you need to make sure that if you have volumes, that the volumes are the same. So we have liters for volume 1 and liters for volume 2, so we're okay. We will leave them, the units, as they are, and we just plug in those units. Okay, so we have 87 times 1000 divided by 425, this whole thing, equals P2 times 500 divided by 300 Kelvin. So the way you would do this, ladies and gentlemen, is you would go 87 times 1000 divided by 425. You're gonna come up with an answer, right? Which is this case, 205, right? And then you would just 500 divided by 300, which is 1.667. Right? And then what you do is, in this case, is we're trying to isolate P2 by itself. And again, the way you do, this is again coming from algebra, P2 times 1.667 is multiplication. So the way that we get P1 by P2 by itself is we divide both sides of the equation by 1.667. All right, which is shown here. And obviously that gives us P2. And in this case, P2 is 123 ATMs. All right, so that is just a pure math in this case. The other thing that you can start thinking about is if there's actually a couple of shortcuts that you can do, but we are not gonna digress over the thing. In this case, if you see a combined gas law problem, it's just figuring out what sides these numbers are gonna go and plugging them into the equation and solving it. Okay, very, very important in this case. So that's the combined gas law, which is a combination of Boyle's, Charles, and Gay-Lussac's law. All right. Another law, Avogadro's law. In this case, we're talking about Avogadro's law, which is the relation between volume and the number of moles. And here's a sample problem right away. It's the number of moles. What is the number of moles? So number of moles, we're looking at N2 that occupies a new volume, V2, when the volume was changed from means V1, and initial number of moles is N1. You write out the whole ideal gas equation again, and again, as previously we have done, we will eliminate the variables that we don't need, that doesn't show up in this actual problem. pressure doesn't show up at all, right? Temperature and the gas constant doesn't show up at all. So we eliminate P, R, and T, which brings us to this equation. Now it's a simplified equation, all right? There's something that I've done which I didn't, like in this case, which I didn't show the intermediate step. Before it was V1 over N1 equals V2 over N2. Our unknown, ladies and gentlemen, is N2. And again, you never ever want to have an unknown in the denominator. The only way that you can do, well, one, there's a complication when your unknown is in the denominator. You actually have to perform a cross multiplication, okay, beforehand. So in this case, I just rotated the variables to make sure that the variables that I need, N2, is actually in the numerator. And again, it's just a simple chug and plug. 0.65 moles divided by 20 times 55. So here is the equation. This is actually the equation here. Okay, maybe I should write this in green. And again, at this point, you should already be familiar with what you should expect. So moles and volume are opposite sides of the fraction bar. One of them is in the numerator and the other one is in the denominator. This means to say that this is a direct relationship, right? So if you increase the volume, what would happen to the number of moles if it's a direct relationship? Well, the number of moles, if it's a direct relationship and the volume has increased, should also be greater. This number should be bigger than 0.65 moles. And if you do that in the calculator, it just so happens that it's almost double. It's actually double. No, more than like, okay, almost double of the initial number of moles. So if the volume increases, the mole should also increase. And that's, okay, and vice versa. And again, the reason why that is because they are on opposite sides of the fraction bar. N is in the numerator and V is in the denominator in this case. And so that is always a direct relationship. Okay, so new problem. What is the new volume occupied by 2.5 moles of gas? All right, so this is N1. Okay, it's actually not N1. It's actually N2. My bad, because it says initial volume. This is V1 and the initial number of moles, so that means it's N1. So again, this is just chug and plug. I am going to leave the equation the way it is. And the reason why, again, is we're looking for V2. And again, if I write the equation the way it is, V2 is going to be in the numerator. So it's perfect. Chug and plug. You should expect the answer that you're going to get. What would happen when the number of moles actually decreases? Well, the volume should also be smaller than 500 mils, and that's the case, 123 mils. And this should make sense according to the kinetic molecular theory. Okay, it's because if you have 1 mole of anything, right, is 6.02. Remember that Avogadro's number. This is actually, that's just why it's called Avogadro's law, times 10 to the 23 particles, right? If I have less than that, what would happen? So this occupies a lot of volume, right? It's like people. The more people you have, the more space they occupy. Now, if I make this mole smaller, what would happen to their volume? Obviously, their volume is actually going to become smaller as well. And that is why this is called Avogadro's law. So if I take a tenth of this, which is 6.02 times 10 to the 22, which is smaller, well, the volume that this occupies should become also smaller. Okay, if I put more particles in, the volume they occupy should be bigger. So again, that should make sense. Henry's law. Okay, this is actually not true Henry's law, but just for our class purposes, we're actually going to do this math anyway, even though it is not an accurate representation of Henry's law. So in this case, how do you know it's Henry's law? Well, let's do some math here. Let's actually do a problem. How many moles of gas? So moles of gas means we're looking for N2. When the pressure was changed from is always P1. 2 is always something 2. So this is P2 and the initial moles. So this is N1. Right? So here's the problem. The units for pressure, for our pressure, are 2 different units. We have pound per square inch and we have atmospheric pressures. So we need to either change the ATM to PSI or the PSI to ATM. I just chose to convert this 2.2 PSI to ATM. And so this is actually 0.15 ATM. So 2.2 psi is actually 0.15 ATM. Okay, so now they are the same units. Okay, and then it's just rewrite the ideal gas equation. We eliminate units that doesn't show up in the problem. Obviously, there is no volume, there's no gas constant, there's no temperature, so all of those variables get canceled out. So we just have N1 over P1 equals N2 over P2. We were gonna leave the way it is, and again, it didn't used to be like that. What happens is you actually have P1 over N1 equals P2 over N2. I just made sure I just flipped it to make sure that our unknown is again in the numerator. Okay, again, remember you can flip these equations as long as you flip both sides. You cannot just flip one side and leave the other side like basically the same. It is the way it is because that you'll just be asking for trouble in that case. Okay, so chug and plug. 2.8 moles divided by 0.5 ATM equals N2. We don't know N2, but we know that the new pressure is 4.5 ATM. Now, this is a direct relationship because pressure and the number of moles are on opposite sides. So again, this means to say when one goes up, the other one has to go up as well, right? So if the atmospheric pressure goes from 0.5 ATM to 4.5 ATM, this also has to increase, which means to say that the N2 has to be bigger than 2.8 moles. And if we do the math, that is the case. All right. So I hope that this makes sense again. And again, this is direct relationships. All right. This is again an oversimplification of Henry's law. Henry's law actually has a lot of other things that's involved. You actually have some constants that this actually is based upon the gas that you have. So each type of gas actually has a characteristic indicated by this constant called Henry's constant. But for our purposes, we just need to take this the way it is and do the math if we need to, okay? For our class, this will be sufficient. And for Henry's law, this should make sense. So we're talking about partial pressure, right? So and we're talking only about like aqueous solution. So if this is an aqueous solution or any other solution, what happens is the way that you dissolve gas particles in it is if you have a container and if you put a lot of pressure on it, lots of pressure, what happens is you are going to get more particles into the solution. Right? If you don't have enough pressure, what happens is you will not be able to push. You're basically, this is basically talking about drowning gas particles in liquids. So if you don't put pressure means you're pushing something down. If you have low pressure, you will not be able to push particles down. If you have high pressure, that means you're going to be able to push a lot of gas particles actually into, in this case, the aqueous solution. This is actually the basis for, in this case, they're called the BENS, okay, or nitrogen problems. But like when you're diving, especially when you're diving, okay. But that is not for a purpose for this class. You can learn about that when you actually encounter that problem in anatomy and physiology. All right. So very important.